Okay, hello? Hello?
Hello.
Okay. Let me. I hope you had a nice weekend. I think it's already recording. Yes. So let's get right into it. Last week, I had said we're not going to go through this differentiation stuff, but I did inquire, and actually, we have to. It's also part of the syllabus. So today we are going to complete Laplace. I had hoped to start Fourier, but I think it will be too much. So we are going to complete Laplace, and then on Friday we will start with a Fourier. Yeah, maybe I'll talk more about it at the end of this lecture. So Israel, please take attendance. I don't know whether this thing keeps track. Just find a way to take attendance. Israel or Joanne, or both of you. You can cross-check on the list afterwards. Yeah, so let's get started. With differentiation and integration of transforms, what's happening? Okay, so yeah, I'll just read from the slide. So it can be shown that if you have a function ft that satisfies the conditions we discussed, I think last week on for the existence of a Laplace transform, then the derivative of the Laplace transform, which is f, which is given by this. I don't remember how we read this, but okay, the derivative of f with respect to s, df ds, can be obtained by differentiating. Yeah, of course, it's the derivative of fs, but it's equivalent to taking the Laplace transform of, what's important is here, the derivative of the transform f of t, okay, can be found by getting the Laplace transform of t times f of t, okay? And that's what this formula is saying. So if, and we're going to look at some examples. I just feel sometimes when you look at the math. So this is just saying, yeah, if this is f of s, its derivative is the Laplace transform of t times f of t, okay? Consequently, yeah, so if the Laplace transform is f of s, if you take the Laplace transform of t of f of, t times f of t, you'll get the negative derivative. Oh, sorry, I had forgotten to mention there's a minus sign. It's the negative. So if you take the Laplace transform of t, f of t, you will get minus f of s. So if, again, I feel like
guys into serial killers, because today I'm going to be talking about one of the most fucked up cases I've ever heard of, the Cargill family.
How is that? Anyway, yeah, so what I was saying is if you have a function ft and its Laplace transform is f of s, okay? If you take the Laplace transform of t times that f of t, you'll get the response. Its Laplace transform is going to be the negative of the derivative of the Laplace transform of f of t. It's a mouthful, but we will look at some examples. So in this way, differentiation of a transform of a function corresponds to the multiplication of the function by negative t. Let's look at an example. This one would have been nice to do on a blackboard, but we don't have one. So we are going to see how we could derive these formulas using this fact that the Laplace transform of t f of t is equal to minus the derivative of f of s. So we have these three. We have these three formulas that we are going to derive, and we shall start with formula 3, and from it we shall derive the other two. So if you look at, I don't know if you've had the chance, I hope you have, but if you look at formula 3 here, you have s over, s over s squared plus beta squared, then square of that. If you strictly look at the, if you look at the denominator for all of these, first of all, if you ignore the squared outside, it should make you think about a cosine or a sine. It should trigger something to do with a cosine or a sine because of that s squared plus beta squared. And the formula we have is similar to this. We have this one at the top. So we have s squared plus omega squared. But if we replace omega squared with beta squared, then the other formula is a bit similar to this. So we start from there. Our assumption here is that since we are going to be using the differentiation, I don't know if you remember how to differentiate such functions. Actually, the formula is down here. You could use this chain rule. You could use this, which is the one which has quotients, or you could use the one where you put this. I tend to prefer the one where it's just v du dx or v du ds plus u dv ds, but you can use whichever. I remember I told you need to remember some of these things, your differentiation, integration, and trigonometry. So if you differentiate this function, you will end up with this. And yeah, actually it's okay, yeah. If you differentiate this, if you substitute to this formula, taking u as beta and v yes, okay. I got confused because I was looking at omega, yeah. So our formula is this. Remember, we are using beta, not omega. So if you take u as beta and v as s squared plus beta squared, that is for sine, okay? Then if you differentiate using this formula, you'll end up with this. I don't know if maybe I can give you a few minutes for those of you who to try and get this. I'll give you 2 minutes to try and see if you get it. Just substitute into this formula and you should be able to get this. I hope you've been able to get to that answer. I don't know if it's 2 minutes. I didn't check the time before I kept quiet. It just seemed like a long time. Anyway, so you should be able to get this for t sine beta t. Okay. Another thing, because remember we are trying to prove this formula, so we have hints here. Okay. We know that if you multiply a sine by t from our formula here, okay, our formula here, we know that the Laplace of f of t is equal to minus the derivative of this, and also that the other statement of it is what? Yeah, anyway, essentially that's it. So on the Laplace inverse of the derivative is minus tft. So if we were given this, right? T times sine beta t. That's why the first thing is to differentiate this sine beta t to get t sine beta t to get this. Okay. So once we have this, to get to our formula here 3, we just need to divide by 2 beta. Okay. If you divide this by 2 beta, you'll end up with s over s squared. I hope that is clear. If you divide this by 2 beta, you'll end up with the required formula, what we needed to prove for formula 3, sorry. Now for these other, let us start with 4, although we can put them in one step. Equation 4, which is we want 1 over 2 beta sine beta t plus beta t cos beta t. So we'll first work out what t cos beta t is. Again, using what we know, we know what the Laplace transform of cos omega t is. We're going to replace omega with beta. So we know that it's s over s squared plus beta squared if we have beta here. So we're going to then have to differentiate that, again, using the same formula that was on the previous slide. And if you do that and plug in the values, in that case, our u will be s and our v will be s squared plus omega squared, plus beta squared. So if you do that, you'll end up with this and your answer will be, remember, there's a minus sign. There's a minus sign here, so don't forget it. So when you do your differentiation, you have to lead with a minus sign here. So when you expand this, you end up with minus s squared, b squared minus s squared, but because of the minus sign here, we end up exchanging terms. So we end up with s squared minus beta squared over the square of this denominator. So the formula we're trying to prove had t cos beta t plus, let's go back to it, I don't remember it. So we had beta t cos beta t, and we have this 2 beta outside. So if we bring it in, it would be 1 over 2 beta sine beta t plus beta plus t cos plus t over 2 cos beta t. If we sum those, because in the previous example we found out what no, we didn't find out. We are going to put these terms together, we are going to sum them. So if we bring in, we are leaving out the 2 for now. So if we have t cos beta t plus 1 over beta sine beta t. Sine beta t, we know it from, again, table 6.1. It's supposed to be beta over s squared plus beta squared. But because we have this 1 over beta, it cancels what should have been up here. So we end up with 1. And then this we have just proved here. So when we add these, ignore the plus or minus. Let's first consider the plus only. When you add them, I hope you can see this clearly, is that because this has a squared in here, we will preserve this term in the addition, the sum, it will be s squared minus beta squared. And because this is only s squared plus beta squared, this up here will be s squared plus beta squared. So you end up with this in your numerator. You end up with s squared minus beta squared plus s squared plus beta squared, and the beta squareds cancel out, so you end up with 2s squared. Okay, so you end up with 2s squared over s squared plus beta squared squared. Okay, but remember our question wanted, the expression was supposed to be just s squared. Right now we have 2s squared. So if we divide through by, we divide this by a half, okay, so that we end up with a half here and a half here, then we will get the desired expression, which will be just s squared over s squared plus beta squared. Now, for formula 2, the signs are reversed. Here you now have, not reversed, but you have minus instead of plus. Everything else is actually the same. The only difference is when you come to this point, this juncture, instead of adding here, you subtract. So what happens instead, you'll end up with s squareds cancelling, and you'll end up with minus 2 beta squared. Okay. Again, if you put the minus sign for the minus fs, and because they want us to end up with 1 over s squared plus beta squared squared. So you have to divide by that beta squared. And if you divide by that beta squared, if you divide by the 2 beta squared, the expression you get after subtract, you end up with 2 beta squared over s squared plus beta squared squared. So to get rid of this term, you need to divide by 1 over 2 beta squared, and you will end up with the desired expression, which will be t cos, will actually be, yeah, t cos beta t. No, I think it's reversed. You end up with, yeah, sine beta t minus beta t cos beta t, yes. And yeah, with that beta cubed in the bottom, because you'll have divided by beta squared. I don't think we have enough time to go through it, like for you to try it out, but maybe I'll send you the steps that are missing, but essentially that's all that happens. We just do the differentiate these terms using that rule, because they've given us what we are trying to prove. We have t cos beta t here. In the first one, we had t sine beta t. So it's just applying that rule, the differentiation rule, and then doing the substitutions in here and simplifying. If you have any questions, now would be a good time to ask. Hello? No questions? Okay. We will go to the integration bit. So for integration, we have that if you have a function ft and you know its Laplace transform is f over s, then the integral of its Laplace transform is the same as getting the Laplace transform of ft divided by t. Okay, so the Laplace transform of ft over t is equal to the integral of, is equal to integrating fs. Okay, that's all there is to it. So with differentiation, it's times t times ft. With integration, it's ft over t. Yeah, this is just trying to prove it, and we don't need to get into that. Just know what the rule is. So we have an example here as well. You're given to find the transform of ln, the natural logarithm of 1 plus omega squared over s squared, which we then turn into an improper fraction, which is going to be s squared plus omega, natural logarithm of s squared plus omega squared divided by s squared. Now, in here, then we apply the what do they call them? They're not laws, but you know those logarithm, how log a over b is equals to log a minus b. We apply that here, and yeah, so we apply that and we end up with we end up with, where are the colors in here? Anyway, we apply that in here and we end up with ln of s squared plus omega squared minus ln of s squared. Okay. And if you differentiate these terms, you'll end up with something which is close to things that we are familiar with. So if you differentiate, because if you differentiate a ln of x, actually it's up here. If you differentiate ln x, you end up with 1 over x. So if you differentiate ln s squared plus omega squared, you'll end up with, first of all, 1 over x is going to be, 1 over x in this case is going to be 1 over s squared plus omega squared. But you remember, because we have s squared inside the brackets, we also have to differentiate it. So we end up with 2s in the numerator. So you'll end up with 2s over s squared plus omega squared. And then for this one, you'll end up with 1 over s squared times 2s. So you end up with 2s over s squared. And then you need to take the inverse transform for this, because these are familiar. We know that this is like, this is for the transform for a cosine, and this is a transform for t. T. So if we take the inverse transform using 1, which is the Laplace transform of f of s, the derivative of f of s is equal to the inverse transform of this, then we will end up with, yes, the s's here cancel, by the way. So this is the same as 2 over s. So, which is what is written here. So if we take the Laplace inverse of this, we'll end up with 2 cos omega t minus 2, which from the first rule down for differentiation, we know was equal to minus t over ft, okay? Hence our inverse, okay, because we wanted ft, we don't want t times ft, then we have to divide this term by minus t to get our answer as 2 into 1 minus, because essentially because of this minus term, we change the signs on here. The 2 becomes positive and this becomes negative. And we divide by t, so we end up with 2 into 1 minus cos omega t. Does anyone have a question? Yes, please. Hello?
I don't understand the question. Is the function given in equation? Hello, can you hear me?
I can hear you now, yes.
Hello?
Hello?
Oh.
Hello?
Okay, so is the function given
Unfortunately, we can't, I cannot hear what you're saying.
Hello?
Yes?
Maybe I'll do.
Hello? No, you cannot talk when
Yes.
she's talking, because we cannot hear you. Let's at least first tell her that we can't hear her. I don't know who is speaking. Ronella, we can't hear you. Even Luna. Who else was asking?
Yes, I was asking
Who
how
is it?
you.
Ronald?
Yeah, this Ronald.
Yes.
Yeah, I was asking how you came to to inverse L from the first step.
The first step is really to denote, say, as this is in the S domain, so it's like the transform, it's the Fourier transform of something which we are trying to find out. Okay, that's the first thing. So we denote it by Fs. Then, because some of these things, it's about figuring out what trick you're going to use. If you take the derivative of ln over ln, if you take the derivative of a ln, it's you'll get rid of the natural log. Okay, because in the formulas we have for finding out the Laplace transform, we do not have any with a log. Okay, so the manipulations that we first do are essentially meant to get rid of the log from our S function, or our function in S. Because if you look at our table, we don't have anything in log. So, but how can we get out of log? We know that if we differentiate a logarithm, a log, natural log, in particular, we will end up with, 1 over x. So by taking the derivative, we know that we'll get rid of ln. And we know from what we have learned earlier is that if we can find the derivative of a Laplace transform, we know what we get in the time domain. We know that we're going to get minus t, negative of t times ft. So we can work backwards, is the issue here. We can first find t minus t times ft, and then we will find ft from that. Okay, so if our fs is this, then we find the derivative of it in order to get rid of the natural log, and we put it in this form, okay? And we find the Laplace inverse of that, it will give us minus t times ft. From the rule that we looked at, which was that the derivative of f of s is the same as the Laplace transform of this, okay? So which means that the inverse transform of this derivative will be t minus t times ft. That's what we are doing here. And once we find minus t times ft, then we know that this is to get ft, which was the question that I wanted ft, did not want minus t times ft. We just divide through by minus t and we get ft. So this first step really is about getting rid of the natural log, so that we can put format, and then also taking advantage of what we know, because if we get the derivative of the Laplace transform, we know what it's equivalent to in the time domain. Ronald, are we together?
Yes, madam. Thank you.
No.
You're welcome. Does anyone else have a question?
The other one.
Okay. I don't know, is Ronella back? Maybe when she comes back to us. Okay, this was an alternative way of looking at it, which is essentially after getting the derivative, we denote it by g of s. It's more or less the same, but let's just go through it. So this is saying after you get the derivative of f of s, you denote it by some g of s, okay? Then you get the inverse transform, which is going to be 2 cos omega t minus 1, okay? And then you then say this was the original function, so you found the derivative, but now you want to integrate it again so that you can get the original f of t, okay? Because to get this, you had to differentiate these terms. So we are saying, okay, this is the same as the Laplace inverse of the integral of g of s, this. And using the integration, again, that we've just looked at previously, we know that if you're trying to get the Laplace inverse of the integral of the Laplace transform is equivalent to getting some term g, in this case it's gt over t. Before we had looked at ft, this was fs, but now it's gs. So this is the same as negative of gt over t. So it's the same, I mean, you end up with the same answer, because if you multiply, if you divide this by t and put a negative in front of it, this will end up being this, which is again what we got in the previous thing. So this is just changing where you approach it. In the one before, we just said, okay, after doing the after doing the Laplace inverse, we know that it's equal to minus TFT. Here, you could take the approach of saying, no, I'm going to try and integrate it again, but I know that the integration again is equal to dividing by minus t, and then you end up with the same answer essentially. So you can use whichever is easier. Personally, I think the differentiation one is easier, more intuitive, but it's the same thing. So maybe I can give you some, what? Could you try to prove this? I'll give you 5 minutes to try and do, prove that the plus inverse of ln 1 minus a squared over s squared is equals to 2 over t to 1 minus cosh 80. I'll give you 5 minutes. And maybe one of you will show us how they did it. I don't know. I don't know if you can share anything. You can take a screenshot and share. So the 5 minutes are up. I hope you were able to. Can anyone share with us what they did, or although I don't know how you would share. Yes, Bonnie?
What I did, are you hearing me?
Yes, I can hear you.
Are you hearing me?
Yes.
Okay, what you do when you're given such a question, you first simplify the question in terms of using the natural guide. Like you find the common denominator, then you separate via natural log. After separating, you have natural log of s squared minus s squared, cross brackets, minus 2 natural log of s.
Okay.
After you have simplified the what?
Natural log of s or s squared?
It will be like the 2 will go down via the natural log. It is the same as what you're saying.
Okay.
Now you have got your simplified f. The first task is to get the simplified f.
Yeah.
After getting the f, you as you know that the derivative of the Laplace transform is equal to the Laplace transform of there is a negative in front into the Laplace transform of t into function of. Then you express this one in terms of that by differentiating both sides of that simplified f of s.
Okay. Yeah.
So you eliminate that derivative via that expression. We used that one of negative Laplace transform of t into function of t. I hope there.
Yes. I hope you're following.
I don't think so if they are following, but let me continue. So you differentiate the right hand side. We're going to differentiate the natural logs, all of them, using the differentiation principles. From there.
So what do you get? When you differentiate, what do you get?
You get 2s over s squared minus s squared. Then minus 2 out of s. Then from there, you can take the Laplace one, the inverse.
Yeah.
From right side to the other side. Now here, this side, when you take the inverse to this side, it's directly seen that the 2 will get out from that inverse, and you remain with the inverse of that one is a hyperbolic cosine of 8t minus 2.
Okay.
Then you remove the negative t from the left side. And then put it to the right-hand side, which it will be below. Then you factorize out the 2 from the right-hand side. And you put it outside. So your final expression will be in terms of t. And it will be f of t equals to negative 2 out of t into hyperbolic cosine of 8t minus 1.
Okay.
Is it that one?
You can then simplify it to look exactly like this. So the hyperbolic cosine goes to the end and the 1 comes in front. Yeah. That's it. At least I know if no one else has understood, you have understood. So that's good. But essentially all he has said is you just go through these steps exactly as we did them here, except now you replace this. No, you go through these steps. Now you have expression. You have 1 minus a squared over a squared. Okay. And once you go through this, you should be able to get this answer quite easily. Okay.
Excuse me.
Yes.
Hello, madam.
Yes.
I think there is a simpler way here.
Is always welcome.
Because okay, if you simplify that lien and you collect the like terms such that you're having s squared minus a squared over s squared, and you simplify lien, you'll be having lien of s squared minus s squared minus lien of s squared, isn't it?
Which is what is here.
Yes, but if you look at this formula I'm seeing up, ideally this lien and the whole function, it came from the integral. Let's first go back.
Where?
To where the question is.
The question is here.
The other one, the question of lien.
It's here. It's the same. It's down here. This is the one I told you to work out on your own. The original one is here.
Oh, yeah, this one. Yes. So ideally, we have this lien is an integral of from 0 up to if when you do that, you will be having
I lost
P
you.
of S.
Hello?
Hello? So if you differentiate lien of that function, you'll be having P of S, isn't it?
You'll be having what?
You will be having the function capital G of S of the Laplace. The Laplace transform of S.
If you want to denote it as G of S, yes?
Yes, you differentiate lien, right? Yes. So if you differentiate lien after simplifying, you'll be having lien of S squared minus S squared minus lien of S. If you differentiate the two, you will remain with 2 of S for the side of lien S squared minus AS. You'll have 2S over S squared minus A squared, and then the other one, the next one, you'll have 2S out of S squared, isn't it?
That's exactly what your former colleague also said.
Yeah, because I heard him when he was elaborating more. Yes,
Yeah,
then
but
you
he
simplify
did
it
exactly that.
and you go back to
Yes, he said exactly that.
okay. Okay.
Okay, does anyone else have a question on this? Okay.
Excuse me.
Yes.
Yeah, I just wanted to maybe share my screen of an image we're working.
But you're telling us the thing that we have seen, isn't it? It's what everyone has.
Yeah.
Okay. Okay, you just wanted people to see it written.
And maybe the visual description would be.
Okay, people who want to take the screenshot, this is the exact thing that we wanted. Okay, I hope they have now. Please stop sharing.
Okay.
Thank you. Okay. So that formula that we have, the one for differentiation, this one, can be used to solve certain types of ordinary differential equations with variable coefficients, okay? And yeah, essentially, if you have an equation like this, of this format, so you have ty dy dt, okay? Anytime you have, okay, no, this is not the formula, but this is an expression. You have t dy dt, okay? You know that you can replace it with this. This was from section 6.2 actually. This is what we looked at sometime last week, okay? So, which is y minus s dy ds. And then remember for this one, we said it is equal to this. So, the Laplace transform of t y, okay, is going to be ds. Oh yeah. So from this, if we take the Laplace transform of this, then we know that we can just differentiate it again and end up with this term. Okay. And if we write y, the Laplace transform of y as y and the Laplace transform of y, derivative of y, then we can write this expression like this as well. Okay. Just look at it and see if it makes sense. So remember that the Laplace transform of y is sy minus, okay, it's given here, is sy minus y 0. This we looked at last week. So, but we know that once you multiply anything by t, it's the same thing as taking the derivative of its transform. So that's what's happening here, times the negative derivative of its transform. That's what's happening here. We are differentiating sy minus y. This is the initial value of the function yt. So, but you know that this is now like, this is a constant. So when you differentiate, it will go to 0. Here, because you have s and y, you use chain rule. So you first differentiate s and you get 1, which is the y here. And then you differentiate y with respect to s. So that's why you end up with s dy ds. The minus then comes in and they're both negative. Same thing here. We know what this is. But once you put t before it, then you have to differentiate in everything and you end up with what you have here. I hope it makes sense. Here again, we multiply, we are going to use chain rule. So we'll have 2sy and then s squared dy ds. Then for this term, we'll just have y, the initial value of yt, which is y0. And yeah, because this is a constant, so we only have s in here. And once we differentiate it, we end up with y0. So you can apply that for certain types of equations. I don't know if you have an example. Yes. One example that I don't really want to go through because I think it's too complicated. But we can just go through it for the sake of going through. But I will not ask anything like this. In fact, I'm not going to go through it because it's just going to confuse people. What I wanted you to note is for types of equations where you have it, this form of equation, we can try to simplify it by using this, applying this, it wasn't a theorem. What should I call it? Not an identity either. This formula, applying this formula is what I will call. I'll just say this formula. So we can, for some equations, just taking them out of the time domain and then putting them in the S domain, then replacing them, it becomes easier to solve than the calculus in the time domain. Yeah, I had hoped to get one that was easier to solve. But essentially for this problem that they just apply that. So, but like I said, you don't have to really understand this one, but I'll just try to go through it to show you. So essentially they replace that where you have t times the second derivative of y. Okay, we replace the second derivative and ty by this term. And then where we have just the first derivative, t times this first derivative, again, we replace by this term. Okay. This one is coming from y times 1. I mean, the first derivative times 1. What we are going to change is this term, minus t times y, which is this term. And then ny is this term. So then you try to solve, or you solve that, you do collection of like terms and simplify, yeah. And then, okay, separating of variables and partial fractions, and yeah, and you end up with this solution based on that, okay? So if you're interested, you can go through it, but essentially that is one application of that. Yeah, please ignore this slide. Slide 128, it isn't important. What I wanted to show you here was just that you can solve this, you can simplify it. It's much easier to solve if you use the Laplace transform of this, and then, yeah, use partial fractions that we've always done, and then do the inverse transform and get the answer. I don't know if there are any questions. This is just an application of what we looked at before. Are there any questions on this? Okay. So we'll look at this. This is the last thing that we're going to look at today. System of ordinary differential equations. How can you use Laplace, the Laplace transform to solve them? We have this where we have like what? We have these two equations that we need to solve. We have the y1 dt is equals to okay, so it's time domain times a11 y1 plus a12 y2 plus some function g1 t. Then y the different, the first the derivative of y2 is also equal to sum this essentially. So what we do is take the Laplace transform of everything. Okay, we denote the Laplace transform of y1 by capital Y1, y2, y2, so g1 by this, g2, and then expand. So we know what the Laplace transform of the first derivative is. It's going to have this format. Then the Laplace transform of all these will be that, and then also that, okay? Again, we then collect like terms and end up with these two equations. And solving, the way we solve simultaneous equations, we can solve this and end up with the required solution, okay? One thing that's also noted here is that even if, I don't know, have you guys done linear algebra yet? I think it's third. No, I think you do it in third year. Anyway, so it's not important for you to focus on the last part of this. It's just a note that even if you can solve this using linear algebra, but I will not give you a question with linear algebra. You can just solve it with the methods you know on how to solve simultaneous equations. So we will look at an example. Unfortunately, the examples in these notes, like I told you, this was someone else's notes. But we can, okay. We can use this one. Although I thought a more appropriate one was the one that used the circuit. But let's just use this example. I didn't want to use this example because I think it's something that would come more natural to maybe mechanical engineers or maybe even civil engineers. But Let's just go through it. So we have a system here. We have a tank 1 initially contains 100 gallons of pure water. Tank 2 initially contains 100 gallons of water, in which 150 pounds of salt are dissolved. LB is pounds and gal is gallons. So that the inflow into T1 is 2 gallons per minute from T2 and 6 gallons per minute containing 6 pounds of salt from the outside. So this is what they are trying to present here. So this is coming from the outside and this is coming from tank T2. And then, so the inflow into T2 is 8, or the inflow into T2 is 8. Did I miss something? Okay, this is just something. The inflow into T2 is 8 gallons per minute from T1. The outflow from T2 is 2 plus 6. Okay, so you have these 2 coming out and this 6 coming out, as shown in the figure. So the mixtures are kept uniform by stirring. So find and plot the salt content. I'm not very interested in these plots. I just want you to solve these equations, which we are going to look at down here. Okay. So from what we have been given, these details given, we could form 2 equations on the rate of change for the rate of change of the the content of tank T1 and T2. Okay, denote 1 by, contents of tank 1 are Y1T, and for tank 2 are Y2T. So the rate of change for Y1, so we have tank 1 is losing 8 gallons per minute and gaining 2 from Y2 and 6 from, we said this was external, so it has nothing to do with Y2. So we have minus 8 over 100, okay, for Y1 and 2 over 100 for Y2, then 6 coming from outside. So remember, tank T1 initially contains 100 gallons of pure water, okay? Tank 2 also initially contains 100 gallons. However, for it has 150 pounds of salt dissolved. So that's where that 100 is coming from. These 6 are coming from outside. It's just where is the 6? Yeah, 6 gallons per minute containing 6 pounds of salt. Okay. Y2, which is tank 2, is only receiving 8 gallons from T1, and then it's losing water to T1 and to the outside. So which denotes this minus 8 over 100 Y2. So it's receiving only from Y1. It's not receiving from the outside. Okay. So initially, Y1 has no salt, but Y2 has 150 pounds of salt. So these are, sorry, instead of expanding, I'm reducing. So this is just writing of these equations, okay? And turning them into and also taking the Laplacian of them, okay? That this is this term, okay? No. Yeah, collecting like terms. So if you differentiate, if you take the Laplace transform of this, the Laplace transform of this, okay, the Laplace transform of everything and collecting of like times, you'll end up with this equation. This is moved to the other side of the, you rearrange it, and this ends up becoming minus 6s, as in when you take the Laplace transform and rearrange. This is minus 0.08 minus s, yes. Remember, we have a derivative here. So, but because the initial condition is 0, this term will not appear. So you just end up with this and this as they appear here. But now with capital Y and the s denoting this derivative. And then here, yeah, we only have y2 because it's just the Laplace transform of the y2 and we keep the coefficient, which is 0.02. Here, because we have an initial condition, when you take the Laplace transform of this, the initial condition of 150 will come into play. Okay? Unlike here, where the initial condition y1 was 0. So when you take the derivative of this term, you'll just end up with y1. But for y2, you will have sy2, and also you'll have y, the initial value, which will be it will be 150. So when you collect like terms, 150 goes on this other side of the equation, it will get the minus from there, and you collect like terms of y2. So you have two equations in terms of y1 and y2, which then you're going to solve. You're going to solve, okay. They used Cramer's rule here, did they? I think they used elimination. You can solve them like learned in HEC, which is essentially write the equation in terms of only one, either y1 or y2, okay? But you leave the s there. So, because once you simplify, you solve them in terms of y1 and y2, you can then flip them using our table 6.1 and find what each term is. And you'll end up with this. If you solve them, you'll end up with these equations. You guys need to go back home and try to get these answers. And then, not go back home, you're at home. And then when you do the inverse transform of these expressions, you'll end up with this. Okay. So please ignore this part. I'm not going to ask you these questions. My interest. Okay, I'll not even ask this question. I'm just looking at it as an example. I think it's too complicated for no reason. But it's just a way for you to work out is if you had this system of equations, what would you do? There's another example that I'm going to show you, which is in the chapter of the book that I review, which I think is more relevant to you as electrical and computer engineers and biomedical engineers. But this one was just to kind of go through the process, since it's already even in your notes, and give you some practice with this partial fraction business. So I hope you go through it. I think it will be good practice for you. So if I were you, I wouldn't focus so much on what they gave us in the beginning. Just imagine you are given two equations, this one, okay, and this one, and given these initial conditions. Can you solve it? Okay. Can you solve this equation? If I gave it to you, if I were to set this question, this is exactly what I wouldn't give it to you as a problem question like this. I would just give it to you like this. I have these two equations, solve them for me using Laplace. These are the steps I would expect you to do. Find the subsidiary equations, solve them the way you'd solve any simultaneous equations in terms of S, and then do the Laplace inverse and find the solution. Does anyone have a question? No? Okay, let's do the one that is more relevant to you. For this one, I may ask you this one as it is, because we have to look at applications, especially in electrical things that are relevant to us as electrical engineers or engineers with a bias to electrical engineering. So this one has to do with circuits. So this is the circuit of interest. I'm sure you guys you've done Kirchhoff's laws. I think you do this stuff in first year. Am I correct? Have you done Kirchhoff's voltage and current laws?
Yes.
Yeah.
Very good. So this is
For computer engineers, we didn't do.
You didn't do.
Yes, they didn't give us that. We didn't do it.
It's not one of your courses.
We didn't.
Okay, that makes it a bit difficult. I thought you guys had. I thought all you guys do these things, but yeah, that's
Circuit theory.
No,
Please.
we didn't do.
Some of us who come from CHS.
Pardon?
Some of us who come from CHS.
From what?
Didn't do. From College of Health Sciences.
Yeah, you also didn't do. I thought you guys would also do something on current. Okay, then it means only electric and telecom people would understand this thing. Would probably get this. But let's just go through it for the sake of completeness. So it means if I gave these examples, I would have to. I cannot give you applications because some people haven't done, which is good. Thank you for the feedback because that was my assumption, and it means you guys would be unfair. I mean, would be unfairly treated. So I see a lot of chats in here. Who are these people chatting in my class and things that? Oh, still. Mohindo, I'm sorry that you can't hear. I hope you will. Maybe you'll hear from the recording. Does anyone else not hear what I'm saying? Okay. Let's just go through it for completeness. It means that what I've got.
We do though.
Okay, good. What I've got from your feedback, is that I cannot give you these kinds of applications because maybe a quarter, maybe a half, I don't know how many you are in the different groups, will not have done this. Because ideally, for instance, when we were doing this course when I was at the university, we were only, I think, electrical students. Then we didn't even have telecommunication engineering. So these things we were expected to do them. And I think even the current syllabus has applications, but you'll find that most of those applications, in the book I gave you, there's a lot of, they have all kinds of engineering because these things apply to all engineering. But if you guys, if computer engineering and biomedical haven't done it, then it's really unfair too. Because this thing assumes that you know what Kirchhoff's laws are, so you'd be able to come up with these equations on your own. I wouldn't have to spell it out. If it was a completely electrical engineering and telecommunication engineering, I would just, essentially, I'll just give them this. I'll just give them this question up here and give them this figure and ask them to do the rest. But what I'm getting from here is I can't do that because, yeah, it would be unfair. So that's noted. Yep.
First time to have.
Someone hasn't muted. Okay, so this is the question. So you have find currents I1 and I2 in the network in figure 145 with L and R measured in terms of the usual units. Vt is equal to 100 volts if 0 is less than or equal to T, which is less than or equal to 0.5, and 0 thereafter. And so the initial values are I0 is equal to 0 and I dt is also equal to 0 initially. So from the question, if I may ask from what we studied last week, when I say Vt is equals to 100, if 0 is less than or equal to T, which is less than or equal to 0.5, and 0 thereafter, what comes to mind? If any of you attended and maybe also went through what we did last week.
Dirac delta function.
Pardon? Beg your pardon?
The Dirac delta function.
No, not the Dirac delta. Dirac delta just takes 1 point.
The unit. The unit step
It is the heavy.
Yes, the heavy side. Yes, absolutely. It's what we are looking at. Okay. But I guess you may have said Dirac when you meant this. So I'll forgive you because you have to remember that the Dirac delta function or the impulse function, it just samples 1 point in the whole function. One. If you wanted to find out the value of a function at time t is equals to 1, you would use the what? The impulse function, because it will just take that point, t is equal to also will be 0. That's how it works. So yes, what we are looking at. Because of that, you should be able to, the first thing you should think about is you have some kind of a subtraction of two step functions. In this case, one is beginning at 0 and the other one is going to a half, 0.5. And that's why you see this here. Okay? So I'm happy that someone at least was able to see that. So you know what this stuff is. So if I had to give you this question, I'd have to give you this equation, it seems like. So from the lower part of this circuit, we have this equation, okay? And from the upper side of the circuit, we have these two equations. So ignore all the details, just imagine I give you a question. This is equation 1, this is equation 1, and this is equation 2. Two simultaneous equations. I want you to, or maybe, I think if I say two simultaneous equations, it's a repetition. So I've given you simultaneous equations in I1 and I2, and I want you to solve them, okay? Again, we would use Laplace to solve it. Of course, here what they did is to first do some simplifications to get rid of the 0.8. They divided everything by 0.8. Yeah, and that makes your life easier, but even if you didn't do that, you would solve it. I hope all of you are aware. So what they did is divide through by 0.8, and for this equation, I think only. And for this one, they just rearranged it, okay? I hope you see what they're doing here. You can understand why there's a space here. It's just to be able to, we're just trying to align everything. So for equation 2, there's nothing on the right-hand side, but everything is aligned. I2 is under I2, I1 under I1, and yeah. So don't mind them. So the next thing is to find the subsidiary equation or system for that matter, because it's more than one equation. So we take the Laplace transform of these two equations and we end up with these two equations. Then we'll solve them the way you'd solve any, because now you only have I1 and I2. Here you still had the derivatives, they're now gone. So solve them the way you'd solve any simultaneous equations and find I1 and I2 in terms of S, okay? Then once you do that, you have this, but you cannot, this is useless to you. You need to put it in a form that is in our table 6.1, okay? So you use partial fractions to simplify it and get here for equation 1. Simplify this and get here for equation 2. Then for this first 0 less than t, which is less than or equal to a half, okay? This is your solution. Now, I showed you some, I hope you got the solution I did for Israel last week. I mean, I did for you guys last week. I sent it to Israel. I hope he shared it with you and you had a chance to look at it. Again, if you use the same manipulation, because you see, according to the second shifting theorem, for t greater than a half, okay, you have I1 minus I1 t minus a half, and I2 minus I2 t minus a half, okay? This is for when t is greater than a half. Again, when you do the manipulations, because you are going to adjust this term, so you'll end up introducing these extra exponentials, okay? From these. And today is the homework I'm giving you. I want you all to work out and get this. This one is easy. I want you to work out and get this. I don't need you to plot it. I just want you to work out and get these ones. And I think you should even send me your solutions. Send me your solutions on Moel so that we appear that we are studying. The university wants to see that you're studying. So this is the homework I'm giving you for this week. I want you to work out up to this. They've given you the solution up to here. Even here I've given you the solution, but I just want you to show me how they got this answer. So t is greater than a half. Please submit it. by our lecture on Friday. Yeah, and this marks the conclusion of our study of Laplacian. There's another example in the notes if you want to. You could also go through it. It's very mechanical engineering. I didn't like it at all, so I'm not going to teach it. But for those who are curious, in every class, there are always those people who want to do everything. So for those who are like that, feel free to go through example 3. But I've only gone through example 1 and example 2 in the reference textbook. And I need that solution, please, by Friday. If you have any questions, please ask them now. I'm ending the lecture today. I'm finished for today. Next week, we're going to start on Fourier analysis. Again, for those of you who are good students, please feel free to go ahead, read ahead. But before we go there, for those of you who have problems with trigonometry, please, I only beg you, go and revise your trigonometric functions, how to interact and integration, because Fourier transforms are even more complex than Laplace, because you have to, they can be simplified, but if the basics of integration of trigonometric functions is difficult for you, both in the exponential form and in their normal form, you will find a Fourier the topic of Fourier series, Fourier transforms very difficult. It shouldn't be. So if you spend the time to remind yourself about these transforms, what is cos A plus B, what is cos A cos B, and those things, and how to integrate a sine and a cosine, and how to, again, the chain rule, then our lesson, because I'm going to be again much faster, we need to finish those things in 3 lessons. By next Friday, we have to have finished Fourier and started something else. But I just wanted to warn you beforehand, it's a bit more complicated than Laplace because there's a bit more manipulations that we need to do. So please be ready. But the concept is more or less the same. Again, you're going to multiply by some exponential and integrate and move a signal from the time domain, the frequency domain. So if you have your integrations and these trigonometric identities and whatever down, then it will be easier. That's my take. So please try to put in the time, and then when I tell you something like cos n pi, okay, cos n pi is equals to -1 when n is positive, and it's equal to 1 when n is, when n is odd, and is equals to 1 when n is even. Those things should come naturally. They should just flow. You should just look at that thing and tell me, oh, madam, this is the answer. And if you don't have that, then that lesson is going to become very difficult. So in advance, please take that. I was supposed to start them today, but I was like, no, I will give you time. I will just let you know what you need to know in advance before that lecture, because then I'm just now going to take it that you have done the practice, ready for Fourier series and transforms from Friday. Please, it's for your own good. Does anyone have any questions? Since we still have like 30 minutes, if you have questions or anything on the plus transform, please feel free to raise it, because the next time you see it, it's probably going to be that test. We're not going to deal with it again in this course.
Excuse me, madam.
Yes.
This is Comrade. For that assignment you've given, do we need to type, or we simply scan and send and upload to MathIII?
You do whatever you want. Whatever is easier for you. If you want to type it,
okay.
But I think for most of you, you want to type in Word. It will be more harm than good for me. If you wanted to type, if you can use software called Leaks or LaTeX, excellent. If you can't, then maybe just write and upload.
Okay.
And you people do it. If you don't do it, what I'm going to do when I come to that class to verify, I'm just going to call on any random name of anyone who is in class to explain to us how they did it. So if you did not do it and you just copied you did not understand it and you copy what someone else did, I will get you. Okay, I may not get everyone, but you might be the unfortunate one that I pick because I don't know whom I'm going to pick. I'll just go on the list and pick anyone. So maybe you can trust probability. Out of the 50, they won't pick me. Or the 60. I don't know how many you'll be attending on that. Today I started with 8 and I have only 46. A pity. But yeah. So please do it. On interest, first of all, it helps us all to learn. It helps me understand where your challenges are. Secondly, it what does it do? It's practice. Because I could bring this question in an exam. This is a very good question. I could give it 15 marks. There's a lot of things that for you to do. By the time you get to the, I give 15 marks, so it makes it easy for me to mark. You know? So please, yeah, please do spend the time and do it. Actually, I can't give 15 marks because I'm not going to tell you to plot, and you're not going to interpret it. So maybe 10 marks. So yeah, there's a bit of work here to do, manipulate, do the inverse. It's an easy 10 marks to get, you know. Please practice as much as possible. I will also try to make it easy for you. Yeah. So where you need to use differentiation, I might tell you using this differentiation rule. I may not write the rule for you. Yes, Julius, iPad. How may I help you? Hello? I cannot hear.
Madam.
My network is off and I found we're talking about.
Which side?
Hello.
Yeah, you still.
Hello, madam.
Yes.
My network was off and you pardon.
You found me talking about what?
An assignment.
Yes, this question that I showed you the last one. We've gone through the steps, but I want you to show me how they got this one, because this is the difficult part of it, or the tricky part, I should say. I want you to show me how they ended up with this solution for time t greater than a half. Someone else has also raised their hand. Mariam Dagir.
Yes, madam. For
Are you the
us,
celebrity?
computer engineers.
Are you
No.
Are you related?
No,
to
I'm not a celebrity. No.
Okay.
Madam, yesterday, for us recently, our representative gave us information that our representative.
For you who?
The computer engineers.
Okay.
We were just given the information recently that we were supposed to be attending the lectures last week with their class.
Hey, but so, Israel, I thought you had coordinated everyone. For you just coordinated electrical engineers.
So that was the problem. Now we are just okay. It's like we don't know anything so far. So far I've been seeing, but I was trying to pick, but the things were not coming out. So is there any time that you can allow us to catch up? Because we also have other lectures and we need to read all the things. We need to also catch up in this lecture, but we don't know what we can do. And yet you are giving an assignment. So we don't know how we are going to do it.
But if you go, Israel, is Israel on? Can you, since you seem to be a dedicated student, the problem is I don't know if people have that, but you can, you are allowed at the university, but if you go to Khan Academy and you look at their course on Laplace transform, they probably even do a better job than me explaining it. Eh? You go and listen to that. The reference book is there on Mowele. Go through it. Actually, you can look at the I gave you some notes. The notes are almost exactly what's in the book, so you can go through the notes, and if you need anything else, maybe go through the book and see what you can do. I can give an exemption for computer engineering students on Friday, but the problem is I had Israel made me believe that he was communicating with everyone. So that was not good. I also started communicating with Joan as a by the way, because I sent Israel a link and it didn't work. She contacted me actually, but it's because I kept sending Israel and it wasn't. So I sent it to Joan just to double check. So from then I was like, okay, maybe I'll just send to 2 people. but I didn't know that everyone deals with their class. Ideally, you people should be working as one class, you know? This business of computer, because when I come to marking, I mark you all the same. And you never know what you might learn from a telecommunications engineer. So especially you biomedical students, I heard you have a challenge. Some of you did not do math in HSC. So if you stay there in your group as biomedical student, I think you do yourself a disservice. If it's possible, try to befriend some of these people and try to go through. What I would recommend is you go to Khan Academy. Khan Academy is very good. They're very good at teaching you the basics of integrals, differentiation, and it doesn't take a lot of time if it's what you have set your mind to do. Now, once you go through that and then you get someone here in maybe telecom who did this stuff in HSC or in electrical or in computer engineering, then it becomes much easier for you to catch up. Okay. Now, for the people of computer engineering, it's a pity that I did not know you guys hadn't attended, but unfortunately, I cannot teach it again. However, like I said, please go to those Khan Academy videos on Laplace transform, sorry, and go through them. If there's anything that's still unclear, you can always send me an email. I shared my email address last time. I'll share it again here in the chat. You can quickly copy it. And then then we can take it from there. Okay.
Thank you, ma'am.
You're welcome. Have I forgotten it? I think it's this one. Let me just double check. Yeah. Yeah, that's it. So in case of anything, you could always, yeah. And for all of you attending the class, you can tell your friends, it's always going to be the same link. I'm not going to change this link. So anytime you need to join the lecture, just use this link. So don't keep asking your class reps for links every week. It's the same link. It's not going to change. Mariam, are you the representative for computer engineering? Oh, please, let me state it this way. Whoever is representing biomedical and computer engineering, please also send me an email or have them send me an email, my email address, so that when I send out the stuff, everyone can get a copy.
Madam,
Yes.
Madam, I'm not the representative, it's Bruno.
It's okay, you just let him know that that's my email address. Let him send me an email so that I put him on the list of class representatives and I can just share with him.
Okay.
Also, whoever is a representative for biomedical, please tell them, I don't know if there's still any biomedical students on the call, on the meeting, but if there's any, please send me an email, whoever your representative is, that I can, when I share that video, for instance, after today's class, I'll just share to 4 people. But now I only have the address of Israel and Joan. So I'll send the video to them and then the recording, and then they can share with everyone else. But the only thing I can tell you, that previously people have been failing this course a lot. So you might have the bias that you're going to fail, but I beg you not to have that bias. The only advice I can give you is try to practice, because the more you practice, the more you become familiar. I don't know about those people who did math in HSC. The more examples you look at, the more things become familiar to you. And then, so whatever exam question comes in the exam, you're able to deal with it. What I can promise is usually in my exam, most of the time, maybe 40% is either an example we did in class or something we did in the test, up to 40%. Because for me, I always want to give people a chance, at least who attended class and who bothered at least to go through the assignment. Although sometimes there are some students who just keep wondering whether they came to study or because they still fail those things. So, and there's a limit to how much you can recycle without seeming unprofessional or unserious as a lecturer. So if you put in the time, you will pass my class. That's all I can say. I will not try to trick you to make you fail. Because belatedly, I realized only African universities do that. Everyone else tries to make it easier for their students to pass without cheating for them. But they try to make it easier for them. So I'm not going to try to explain anything in a way to confuse you, or I won't try to set questions to trick you. No. If you can understand what we learn in class, ideally, of course, usually my exams have one hard, difficult question. That one I will not lie to you, which I don't expect any student to do except one who is really sharp. But then most of the time, if you have attended my classes and you are a serious student, you cannot fail to get above 70 or even 80, sometimes 90s. So yeah, if you work at it, you will not fail. It's not my intention to have 50% of the class to fail. But if you don't do your part, then it will continue as it has always been, that some people will fail. But for me, my promise, like I told you, if you attend class, go through these examples, please go and go through the examples that we go through in class. And if we do a test, make sure that you go. I always give my marking scheme to students so you can see how the solutions work. Go through the marking scheme. Then you'll be assured of getting at least 40%. Now you have to look for at least 10%. Just 10%, you will not fail. Okay. Have a nice week. See you on Friday. Unless anyone else has a question.
Excuse me, madam.
Thank you. Yes.
Madam, will you kindly upload the Fourier transforms notes on Mwele before Friday such that we can have a chance to look at them?
I'm going to upload the book. Okay?
Yeah, thank you.
Yeah, I'm going to upload the chapter. Then you can look at it. That will be very good. I'll be happy if I find some people who are familiar with it. I'll put them on notes maybe by end of tomorrow. Okay? Not today. Yes. But don't worry, even if you come when you haven't gone through, what I've told you, what you need for it is just practice your trigonometry and your integration. Yes. Once those two are good, you will be good, because it's just a lot of integrations and trigonometry. Because the basis of Fourier transform is simply is that what Fourier said is that if you have a periodic function, any form of periodic function, you can write it in form of a series of some cosines and sines. So unfortunately, there's no way around trigonometry in there, and unfortunately, there's no way around integration. Integration and differentiation. So mainly integration, but because they are one or the other, you cannot miss out some form of differentiation somewhere. Especially even when you're doing integration, when you're using the chain rule, you have differentiation in there. So these two go together. So that's what's most important. If you don't get them before Friday, don't be very upset. Just practice these things and be familiar with them. Then everything else will be easy. Any other questions? Okay, have a nice week, like I said. I'll see you on Friday. I'll talk to you on Friday.
Thank you. Nice week too.
Thank you, bye.
Thank you.